the process control during laser powder bed fusion. And it's really well in the continuity of your talk. So it's really a result of a team work. Basically, all the AM Linde team contribute to this study with different alloys. And as well, we have a partner in France, 3D MATLAB, who is also developing this gas with us. So just a few words about Linde. So Linde is the leading industrial gases and engineering company. So the core business is to deliver gas, as you can see on this nice picture, worldwide. And also Linde has several development centers, and we are part as the AM Linde team of one of these development centers. And I will show you our lab. So this is how the Linde AM team lab looks like. So we are located close to Munich. Currently, we are 4 technology experts and 4 PhD students working on several gases and alloys typically, 1 director and 1 technician. So as you can see here on this lab, it's dedicated to laser powder bed fusion machine. We have several different types of machines, and we also Trumpf machine and an Aconity Mini, because each machine has its own way to handle the gas flow, so it's interesting for us. And we have a brand new lab with a binder jetting printer, and we also are working on a small-scale metal atomizer lab to assess the gas parameter. So in addition to the machine, we have various analytics for the powder and the parts, to control and monitor the powder quality before the job, after the job, all the time, and as well to check how the parts look like. We have a metallographic lab. Yes, on the binder jetting printer, don't miss the poster of our student Kai Zisser about the reusability of the 4 pH stainless steel powder.
No.
Thanks. So the goal at Linde is really to cover the whole AM value chain, so from the powder production to the post-processing, and in between we have the powder handling and the 3D printing, because gas is everywhere in the AM process chain. So, but today we will focus on the 3D printing part, and I will try to cover different alloys to cope with the topic of this conference, alloy in AM. So, I guess we can directly start and dive into the gas. So, what is the role of the process gas for additive manufacturing? So, at first, in your printer, you had air, and you need to purge air to have the nice atmosphere. So one of the main goals is exactly to have a protective atmosphere during the job to avoid oxidation. A second role is to apply a constant process gas flow over the powder bed to remove the fumes and the projection. This is also what you can nicely see here thanks to shadow graphs. You see the effect of an addition of gas flow to remove the fumes and the projection. There is usually also a needle gas flow at the top of the chamber to keep clean, the laser lenses. So, in a few words, the roles of the gas. Now, and it's what we have just seen, we can directly visually see what happens when you change the process gas. Here we were using an aluminum alloy 2000 series. So on the left-hand side, you have the same job printed under argon, in the middle under helium, and on the right with CO2. Argon is the usual process gas. You see the spatters, as already mentioned. You can, I guess, already see that with helium, we generate much less hot spatter. And with CO2, it's like a firework. It's not an inert gas anymore, so we have a highly reactive phenomenon. So we will focus now on the both argon and helium molecule. So why printing with a mixture of argon and helium? What is the difference? So that's already been a bit covered. mainly, what is different between argon and helium is the density. Helium is 10 times lighter than argon, plus the lambda and the Cp of helium is 10 times higher. So this combination of parameters will really help to mitigate the heat accumulation above the melt pool. So you always have a recoil pressure that leads to process byproduct, and you have also fumes that are generated. But with helium, and this is only pure helium, the recoil pressure is reduced, so this will lead to less byproduct ejection and less fumes. This will lead to decrease the amount of hot spatter and all the byproducts. So you mentioned, yes, helium is expensive, so that's why we wanted to develop a mixture of argon and helium to have the benefits of helium, but not to the expense of the cost. And as well, with only helium, usually the printers are designed for argon, nitrogen, and the pump are suffering with pure helium, which is so light. So that's how we try to define the best balance with a mixture of argon and helium. So we move to the titanium 6-4 here. It's again a picture thanks to Schlieren imaging technology. So here you can see on the left-hand side, you will always see what happens on the argon, and on the right-hand side with our mixture of argon and helium, which is named Advanced Laser 230. So thanks to the Schlieren imaging, you could really see what is usually invisible. So you have all the vapors, the fume, plus in white, you have the incandescent spatter. And thanks to these pictures, we were able to really quantify the amount of hot spatter. And with our gas mixture, we could see that we reduce by 35% the amount of incandescent spatter. I won't take more time on that because Camille Pozon has a keynote tomorrow about that topic, and you will learn more about that tomorrow. And as well, Armand Raza also has a presentation tomorrow dedicated to the spatter formation and the difference between different gases. So another way to visualize this hot spatter, because the hot spatter might create some defects because they will stick on the surface surrounding the parts, and this might create some defects layer after layer. So this will have an impact on the porosity. So we use here what is called the OT monitoring system. So OT meant for optical tomography. This is an equipment from EOS that we have on our EOS M290. And basically, it's a camera which is observing the entire building platform at all times. And here you can see the different picture correspond to the scanner laser direction, which is changing layer by layer. And I guess you can also see that if you compare the same cubes printing under argon and printed with Advanced Laser 230, we see that the spatter is spread over a scarcer diameter around each part. So we have less repartition of the hot spatter around the part. And you can imagine that each line corresponds to this incandescent spatter that can lead to a defect. It's still from an OT monitoring picture, but here we wanted to have a 3D images. So you have layer by layer all the hot spatter that are visible. And what we also did is that, so this is like a series of 8 cubes printed under argon, the same under the Advanced Laser 230, and we changed the parameters from the EOS standard parameter to what we call the fast parameter. And you will see that this will also have an impact on the density of the part. So density, we wanted to measure the density of our part. Here's a nice lattice structures. To do so, because you can't really proceed with the usual cross-section of your part, so we did a micro-computed tomography so that we have a volumetric assessment of all the pores into the part we produced. So this is how we could calculate the porosity content. So for each type of lattice structure, diorite, dodecahedron, or trabecula, and if you compare the porosity of this structure printed on the argon with the same structure but printed with our new gas mixture and our fast parameter, we have a reduction of the porosity of 70%. So, new alloy, Inconel 718, we did the same type of study using OT monitoring system. So it's a new, it's another layout. And again, we wanted to highlight and quantify properly the formation of spatter. And you can see here the difference between pure argon and pure helium. And you see again that we have less spatter emitted around the part and on a shorter distance. The next slide, you will see the effect from argon to helium, the effect of increasing the amount of helium, and you really see, you really can see that you have an improvement when you increase the amount of helium into argon. With pure helium, yeah, we could quantify that the reduction was around 60%. So now the impact again on the quality of the part. We are still with Inconel 780. So if you print Inconel 780 with standard parameter on the argon and on the helium, and in between we have an increased amount of helium. You can see that with the standard parameters, you always have a nice density. But now, if you try less energetic parameters, typically lower power or higher speed, you can see that with pure argon, the usual process gas, you have a bad density. And if you increase the amount of helium, finally, you can have a quite nice density. Even you increase the speed or you decrease the power. Because you remember, with helium, we can decrease the amount of spatter, we also decrease the fume. So there are less byproducts that will shadow the laser beam. So this will lead to a more powerful process, even with less energetic parameter. So we have seen the effect of process gases on an aluminium alloy, on titanium 6-4, on Inconel. So we also work on this aluminium silica 10 together with EOS. And recently we work on nitinol, and if you are interested, we will have another presentation at World PM. And we also see the nice effect of an addition of helium on nitinol. So we can fairly say that this addition of helium is alloy agnostic, and it's really the effect of the gas that is helpful. So as a summary, if you compare argon and an addition of helium into argon, it will lead to more stable process, meaning less incandescent spatter, less byproduct. So this will help to have a better surface quality, meaning less risk of defective parts because we have less redeposition on the layer. And less byproduct means less laser disturbance and faster printing. So this combined leads to the reduction of post-processing effort because your surface will be smoother, and also an increase of the reliability and the productivity. And again, it's alloy agnostic as far as we have observed at the moment. Yeah, so we try to throw some example on different alloys. And thank you very much for your attention.